Okay, so hello everyone to the next webinar in our Taylor Hobson webinar metrology series. I'm Nina Hennemann from LuphoStraight Taylor Hobson, and I'm going to talk about software-assisted alignment and measurement of segmented surfaces by LuphoScan. How it works. So here you see me. I'm working as a senior application manager, mainly focusing on training at Luphos or Taylor Hobson Luphos. I'm working with this instrument now for about 8 years, and my background is from physics. So I have a master's degree in physics, mainly focusing on optics. And yeah, through Luphos, I came to metrology. So what's the content of the seminar? Maybe some of you have already watched a seminar 4 weeks ago from my colleague, Dr. Mark Wendel. So he explained the basic principle of our LuphoScan measurement device, showed you what the instrument is capable of, what measurements we can do. And now, starting with this webinar, we will have a series of webinars giving you more detailed information about the special measurements you can do on software modules. I now will first start with standard measurements of Aspheres on the LuphoScan, but even though also for the people already knowing the LuphoScan, there's something new because we have now a semi-automated alignment helper that is called LuphoStraight. We had LuphoStraight in the past, but now it's much better, and you will see how it will make your life easier aligning Aspheres. Then I will go on and present the software module for annular lenses. That means lenses with a central hole. And after that, I will show you the software module for segmented lenses. Also, this module might be known to some of you already, but with newer software versions, we now have a lot more masking options than in the past. Okay, let's start with Asphere measurements. So the LuphoScan platform was designed for measuring rotational symmetric objects. So whatever it comes like Aspheres. If you can describe them with an aspheric description, you're usually able to measure it. If it's a rotational symmetric full surface, then it's a standard option on all our LuphoScan platforms. There are no limitations on the slope, so we can go up to a full hemisphere. And there's also no limitation on the spherical departure. So we don't mind if it's a real asphere with a gull wing shape and points of inflections, for example. How to tell our software what we want to measure? So all you have to know is the aspheric formula of your part. So you need to know the radius of curvature of your part, the conic constant, and the aspheric coefficients. That's actually the main information you have to input to our software. Our software then has the option to use a SAG table to check if you made any typos, for example. But the most important information is the trajectory that you get by entering the aspheric formula. If our software knows the shape of the surface, it knows the trajectory, but you could have entered the part in different heights inside the platform. So what you also need to do is you need to find the height. That means the position of your object inside the platform. And I have a little video prepared that's going to show you how you enter your asphere and how you find the height. I always say you enter the asphere, but if you have done it once, you can save it as an object and then you just load it into the software again. So if you have a group of always the same lens, enter it once, save it as an object and measure it again and again. So that's the video. So now I'm just loading an object. Here it's the reference asphere, and you've seen all the fields have been employed with the radius of curvature. And now I need to find the height. And this is done manually the first time if you have no idea where your part is inside the platform. If it's always at a similar height, the software is able to use the value already entered here and just correct it. So what's happening now, I'm using the probe to move down close to the object, monitoring the signal strength in between, And when I'm close to maximum of signal intensity, I can use my button peak height to find the real maximum of intensity, and the software automatically will change the height value, and we know where the part is in the platform from the height, and we know the surface shape. So after we have defined all of this, we have to take care of alignment sometimes. It depends a bit. If you get your part directly out of your production diamond turning machine, whatever, it's usually glued to an expansion arbor. If that is the case, you just take your part, place it into the hydraulic expansion chuck of our platform, find the height, enter the aspheric formula, you're ready to measure. If you have a free object like you've seen in the short video before, I've just placed it on the center and level table, so it might be that it's a bit off center, probably it's a bit off center, and it might be slightly tilted. So in the past, this alignment was done manually, using the probe, using indicators, on different ways. But now we have the semi-automated possibility. So again, I have a little video showing you that. And it's called the LuphoStraight, and it's also included in all basic software. So what you need to do is you need to enter the part, enter the aspheric description, find the height, and then in the LuphoStraight window, you just press quantify. And what's now happening is the software has thought about two different diameters where it's moving to. It's going to rotate the part, and out of the signal of the object probe, it's going to calculate the misalignment of the part. Because we now have the feedback from the object probe, we know the description of the part, so we can find out the tilt and off center. So you get the values here. And now what I can do is I can also correct it. So I just have to say, now I want to correct tilt X. I turn the tilting knob of my center and leveling table, and I get a live feedback. And by looking at this number, I can easily level it to less than 10 or 5 arc seconds. Wouldn't even be necessary that good, but it's possible, and it can be done so easy. As you can see here, it's really just a few seconds, and your part is aligned very well. So now I do the same for the centering in X. I go to the centering in Y. You can see the spindle rotates so that I have the right knob in the direction of measurement. And now I'm just going to repeat the LuphoStraight measurement to check that the values really are good, or to prove that. So again, we're going to the first diameter. The spindle is going to do a full rotation. I'm collecting data with my object probe. I go to the second diameter, do a full rotation, collect the data. And in the end now, my tilt is less than 5 arc seconds. My off center is around 1 micron. Really easy, really fast to align my part. Now that the part's also aligned in the platform, of course, I can change some settings like the pitch for the measurement, but if I want to, I can also start directly measuring the surface of my part. So with one click, I will get the full 3D topology. And that's the next video I'm going to show you. So in here, you can already see the trajectory. We have a gull-wing Asphere. And now if I just click start in the software, the probe is going to move to the starting position. When the probe is moving down to the object, it's going to monitor the signal intensity. That's just some kind of emergency stop, because if I would cross a maximum of intensity while going down, the probe would abort the motion and give me a warning. Now that I'm at a starting position, the rotation starts. The software starts to acquire data. And I just sped it up because we don't want to wait 5 minutes looking at my part to spin. So now I'm doing the full surface. You see, there's no problem with the point of inflection. The probe just follows the design while rotating. And after the measurement is finished, my view is going to change, and I'm going to the output window. And this window is now giving me my full 3D form error. I get a 3D view, a top view, and 2 cutaways in here. This is all the deviation from the design curve. In this window, you can see that the tilt and the off-center that is calculated now by using data from the complete surface is almost the same as for the LuphoStraight, which only did 2 rings on the measurement. We get out a best fit radius, we can get the power of the part, the peak to valley, we can get RMS, slope values, and there's also evaluation according to the ISO 10110 if you want that. So as you can see, measuring an Asphere, quite straightforward. You just need your aspheric description. You need to find the height at least once. Maybe you need to do some alignment if your part is not on an expansion arbor, but we have the alignment help, LuphoStraight for that, and then you can do the measurement and get your result. So now the next topic, annular lenses. This is a software module. What are annular lenses? Annular lenses are objects with a concentric hole, like you see on those pictures. The challenge here is, as you have seen during the measurement, we usually start a bit shifted to the center and measure the full surface with the trajectory. Now in that case, when measuring the full surface, we are crossing this hole in the center. That means our signal is going to be interrupted. For a single wavelength interferometer, that would be a problem. But the multi-wavelength interferometry that we are using can do absolute measurements. And that's why we are able to measure on those interrupted surfaces. And for those parts, we still have a form measurement accuracy of up to 13 nanometer PV. It depends a bit on the size of the hole for annular parts, but for most of them, it's possible to reach 30 nanometers. So how does the trajectory look like for a part of this? How do we input it? We input it the same way that I showed before. We need a radius of curvature, conic constant, aspheric coefficients. We're defining the diameter for the measurement, and the new thing is that we're also defining an annulus. That's the diameter of the central hole, what you see here as the flat surface. Sometimes it might happen that you're not really having a hole, but sometimes sticking out in the center of your lens. And in that case, what you can do is you can use what we call here an annular barrier. So in that case, we're going to measure on one side of the hole. We're moving up by the value defined on the annular barrier, cross the hole, go down and measure the rest of the surface. So here we can make sure that we're not going to have a crash. And this software module can be combined with other software modules like the segmented lenses that I'm going to show afterwards, or the spherodiffractive lenses and the freeform modules that you're going to see in the other webinar series. Now I'm going to show you how a measurement and a result will look for an annular Asphere. So again, we just start the measurement. The probe, now I skipped this, moving down is already at the starting point. And when we're rotating, the yellow line here shows you the signal of the object probe. And it's a sign because the object is not perfectly centered. And when I cross the hole, it's just some data crap because I don't have a valid signal. But when I'm back on the surface again, I'm having my sine wave again because the multi-wavelength interferometry doesn't care about the interruption in between. After the measurement, I directly get an output of the form error of just the annular part. The hole doesn't need to be masked. The software knows there's a hole in the center, and that's why you're directly having your output and the hole is masked. You get the same information as before, the off-center, best fit radius, the PV, all the information that you can get for a full surface. Measuring annular lenses, as you can see, is as simple as measuring full Aspheres, and also here you're able to use the LuphoStraight tool to do the alignment. Next topic, the segmented lenses. So the difference between the annular module and the segmented module is that for the annular module, we're going off the surface once and we're going on the surface once. Segmented lenses for us are objects with a non-circular aperture, as you can see here, D-cut shape or rectangular lenses. And it might also be that there are just interruptions on the surface that are not concentric, like a hole on the side or several holes. So anything like this we call a segmented lens. And it doesn't matter if it's a freeform or it's an Asphere. The module works for both. Again, the challenge is that during the measurement, we're going on and off the surface all the time, and we're only able to do it to deal with this interrupted signal because the capability of the multi-wavelengths interferometry to do absolute measurements. Also here, the form measurement accuracy can go down to 30 nanometer peak to valley. What's new in this module? In the past, when we measured segmented lenses, we just masked by using the signal intensity. So we compared the data points on the surface that had signal intensity because light is reflected back into the probe with the points off the surface that either have no signal at all or very low signal because we are outside of a polished area on the part. Now with the new software, we cannot just set a lower threshold saying, okay, any data point with less intensity than, let's say, 0.25 volts is masked. We can also set an upper threshold saying if the signal is too high, we want to mask that. New is also that we can have a masking by deviation from a Zernike fit. So what's happening here is your measurement is showing you the form error, so the deviation between design and the measurement. What we're doing now is we're using a Zernike fit to the measured data, and then we compare the Zernike fit with the measurement. And if there's a deviation that's bigger than what we set, we will mask it. Very handy is also the rectangular masking. In that case, you define the width and the height of your rectangle. You can position the rectangle in your area. It doesn't need to be central. You can shift it in X and in Y. And you're also able to tilt the rectangle. And then there are two options. You can either say you just want to use the data inside your rectangle, or you're going to mask the data inside the rectangle and use all data around of it. That's what meant here with the invert. And quite similar to the rectangular fit, we can also use a ring. In that case, we define an inner aperture, we define an outer aperture, what gives us a ring. We can again position the ring in our measurement area, and we can also say we don't want to mask a full ring, we just want a segment of a ring, so we have a start and stop angle. And also here we're able to either look at the data inside the ring or at the data outside of the ring. Both is possible. And then it's possible to use 5 of those masks simultaneously. You can use different rectangular masks everywhere. You can use a signal threshold mask, and maybe there are some leftover data points because the difference between clear aperture and non-polished area is not so big. So you can use rectangular masks to optimize that. And again, I have a little video showing a measurement of a segmented lens. The input again works the same as for a full Asphere. So you need to enter the aspheric description, and then the measurement will start, and the software will pretend that it's a full surface. It will still rotate and still collect data points during the rotation. Even though when it's not on the surface, again, you will see it here in the signal of the object probe that's represented by the yellow line. While I'm on the surface doing a full rotation, this is a nice sine wave. When I'm going off the surface, you will see big steps and spikes, but we're always coming back to the original value because we are using multi-wavelengths interferometry. Okay, so after the measurement is finished, our view will look a bit strange because we're still seeing all data points, the one on and off the surface. So what we're going to do is we have to look for the signal intensity. So we change to signal intensity and we check how much signal do we have on and off the surface. It's about 270 millivolts. Then we can open the masking window, look for a signal threshold mask and set a threshold of about 0.2 volts. And now when we evaluate again, all data points with less signal than 0.2 volts are being masked, and all that's left over is our part. Again, we can get the tilt, the off-center, the peak to valley, the RMS, all the information you would want from your part. Okay, so in summary, what have I shown you in this short seminar? So we started with measurements of full A-spheres, and here I want to emphasize that we have a really nice tool, the LuphoStraight, which helps us to do a really quick alignment of the lens, because it not only gives us the tilt and the off-center value for the sample, it also will give us live feedback to compensate for tilt and off-center in both directions. Then I showed you we have two different software modules to deal with interrupted surfaces. First of all, it's important that we're using the multi-wavelengths interferometry to be able to deal with the interruptions at all. Then I showed you we can measure annular lenses with a concentric hole, and we can measure segmented lenses with a non-circular aperture. So thanks all of you for your attention. If you have any questions, you can go to our website or send me an email directly to this address. And I also want to advertise our next optics webinar. This will be in 2 weeks, and my colleague Dr. Yang Yu will hold this webinar about cutting-edge measurement techniques of diffractive and Fresnel optics. So thank you for your attention again, and have a nice day. Goodbye.